So today we'll talk about chapter 6, which is also related to the next lab we'll be working on, which is lab 6. Now this will be the first lab where you will see some real application that we can try with the digital circuit. So remember we learned about how to do the Boolean addition, right? Using some Boolean rules, okay, and we know how to do that. But today we'll actually look at a circuit which can implement those rules. That means this circuit can add binary numbers. Just like the way you see the rules, this circuit can add the binary numbers following those rules, okay? So this circuit in short is called half adder. The reason this is called adder because as you can see this is adding numbers, right? That's why this is called adder, and I will we'll shortly explain why this is called half, okay? So let me show you a quick example. If you can recall, or if you can just open that page where you have all the Boolean rules for the binary addition, you probably will be able to notice this. Let's say if you have 2 bits, how you add? When you have 0 plus 0, your sum is what? 0, right? And your carry is also 0. So we actually wrote all of those from the rules, okay? So that means this is exactly what we want to get from the circuit. If we do these additions, we want to get all these bits as our sum and all these bits as our carry, because remember if you add 2 bits you get a sum, you also get a carry, right? In some cases there is a carry, some cases there is no carry, but you actually have to consider carry because there is a chance that there will be carry in some cases. Now if you look at more carefully this circuit, and if you look at this column, it's actually very simple. All you have to do is, for this column here, this pretty much look like an AND gate, right? If you can think, this is just an AND gate, because AND gate gives you high only when both of these inputs are high, right? So that means your circuit for the carry is nothing different than AND gate. And if you look at this column carefully, this is pretty much is matching with the exclusive OR gate. If you recall, what was the characteristics of the exclusive OR gate? Exclusive OR gate gives you high when both of the inputs are different. When both of the inputs are different, right? So you see here in this row both of the inputs are different, and the third row again both of the inputs are different, so it's 1. So that's what we did here for both A and B. We actually simply have drawn an exclusive OR gate for the summation and an AND gate for the carry, and that will do the purpose. It's very simple. So from now on, instead of drawing this whole circuit, we'll actually use a symbol like this one. Now anytime if we draw this symbol, then you know that we are actually trying to draw this circuit. So instead of drawing the exclusive OR gate and AND gate again and again, we'll just draw this rectangular box with A and B here, and we'll write a sum sign here, we'll write a carry out sign here, so you pretty much know what exactly we are trying to draw, okay? So this actually means this. Now, so you can see how we can really implement the circuit which can do the binary addition of 2 bits. Now if you look at more carefully what exactly is missing here, let me go back to that one again. What is missing here? Think about the binary addition. A lot of times this happens that you may have a carry from the previous column, right? Because when you are adding, you might have a carry from the previous column. So in that case, you will be actually adding 3 bit, not 2, because you have to add A plus B and also the carry you got from the previous column, okay? Which is actually missing in this circuit. That's why this circuit is called half adder. To make it full, we'll actually draw again a similar circuit which is called full adder, but in this case we'll have 3 inputs, because we'll have A and B, and we'll also have a C in. Now C in means the carry from the previous column. Now I'm not saying we'll get a carry from the previous column. We might have a carry, we might not have a carry, but we have to keep the provision that so that we can get the carry. Okay. Now since we have 3 columns of input this time, as you can guess, we'll have 8 combination of the input, because it's just simple 2 to the power 3, so the 8 combinations. And if you can read using the binary numbers, all these are actually the raw binary numbers. This is the binary 0 and binary 1, 2, all the way to binary 7. So we actually have written all those 8 numbers from 0 to 7. That's exactly all the time we do. And then I tried to write all the output here that we should be getting, and all this carry out and all this sum actually I wrote using the Boolean rules. If you can go back to the binary addition rules, you will see that we actually first tried to write the rules for 2 binary bits. Later on, we tried the addition for 3 binary bits. The reason we did the 3 because we know that we might have a carry from the previous column, okay, which actually completes the whole thing. Okay. Now to make a full adder, all we have to do is we actually have to combine 2 half adder. Remember in the last slide we talked about the half adder? So it's actually very simple. All you have to do is just, as you see, these are the symbols for the half adder, right? Remember? Now this symbol actually means that there is an AND gate and exclusive OR gate inside the symbol. So this is a half adder. So all you have to do is you have to just combine 2 half adder, and one of the sum will be connected here as A, meaning you are adding 2 bit, and that is the sum of the 2 bit. But you are not done, because you also have a 3rd bit, right? Because that might be the carry that you are getting from the previous column. Now that 3rd bit is actually here, C in. Now that 3rd bit is added here as your B, and then you will be getting a carry out from here. You might be getting a carry out from the previous column, and both of the carry out is actually ORed here. The reason is, if you have a carry from either of this column or both of this, I'm saying either of this half adder or both of this half adder, you will actually end up having a carry. That's why this is there is an OR gate, and this is the final sum. Now think about the final sum. What exactly we are doing? We are first adding A and B in the first half adder. In the second half adder, we are adding a C in with the A plus B. So that means you are actually doing this, A plus B plus C in. And you are also taking into account of the carry you might have when you are adding 3 of this bit. So this actually completes our full adder. Okay. Now that means to make a full adder, we are actually combining 2 half adder and a little bit of additional circuit like with an OR gate. So from now on, instead of drawing this whole thing for the full adder, just drawing 2 different half adder, we'll just use a single symbol, which is again a rectangular symbol where we'll have 3 input instead of 2, because this is a full adder. A, B, and C in. Remember, C in should be something coming from the previous column. And then there will be a sum, there will be a final carry out. Now, anytime if you see this symbol, that actually means this circuit. Okay? To make it simplified, we just use the symbol at some point. Now, again, I tried to still draw the half adder so that we understand things a little bit better. Now in this case, I'm just trying to do a little bit of experiment to show you how exactly it works for different inputs. So let's say this is a full adder, right? So we are just showing 2 half adder and an additional OR gate. So let's say how it works, we want to see it. So we have 2 inputs, A and B, and then this is a carry which is coming from the previous column, which is a 1. Okay. Now this is how exactly it should be working. So if you are adding 1 and 0, your sum should be 1, right? And your carry should be 0 here. And then this sum is added to the carry again here. So now you are adding 1 plus 1, so your sum should be 0 and carry should be 1. Now if you look at this one, you have a carry of 1 here and you have a carry of 0 from the previous column, so that means the final carry should be, final carry should be 1. Okay. Now if you want, you can match with the binary rules that you have learned for the Boolean addition. So pretty much this is the sum of all those things. Okay, so you just want to double check how the full adder works. Now you can also make a parallel adders combining some full adders. Now what exactly we are trying is, so far whatever we have seen that actually can add only one bit, right? Like A plus B plus C in, that's just one bit, right? Now how about if you have a number which is like 4 bit long, right? You are adding 4 bit plus 4 bit, right? So that means I'm just talking about this sort of numbers. Like let's say you are trying to add two numbers. Let's say the first number is 1101, right? And the second number is, let's say, 1001. Okay? So each number has like 4 bit, right? So how do you add it? So you actually need, so to add only one single column, you need one full adder. That's what I'm saying? Since you have like 4 columns of number, you actually will need 4 different adder, meaning full adder. So I just tried to draw a 4 full adder, which is also called parallel adders, okay, which can draw 4 bit of binary numbers. Now the computer that you have in front of you, those are again some digital circuit which can add at least 64 bit long numbers, because these are 64 bit computers. So think about this, you actually have 64 of these adders instead of 4, but the idea is still the same. Okay. Now how this bit work, meaning the adder work, is still the same. So every time we are actually taking one bit from 2 numbers. Okay. So that means your rightmost bit from the top number is, let's say, A1, and rightmost bit from the bottom number is B1, right? So the next one is what? B2, and this is the A from A, that would be A2, and then A3, B3, right? So that's how it will go, right? So you are just adding one set of those bits every time. Okay. And at the very beginning, you are assumed there might be some carry from outside. Most of the cases, that carry usually is 0, because there is usually no carry at the very beginning. So, but we still keep the provision so that if you have any, you can always keep it. But every other time, if you see here, we are adding these 2 bits and we are getting the sum. But whatever the carry we are getting, that carry is actually shifted to the next column. This is exactly how we add, right? Remember, when we add a column, what do? If you get a carry, you put the carry to the top of the next column, right? That's exactly how we are working here. See, we are getting a carry, and then we are putting the carry at the top of the next column, like part of the next column. So that's exactly how we are working, and then at the very end, you'll end up have a final carry. The final carry might be 0, might be 1, but you still have a provision of keeping it. Okay. So this is also called 4-bit adder, 4-bit binary adder. Now, in reality, we actually have a circuit. We have an IC which combines all these 4-bit adders. Okay, that's a single IC. The number of the IC is 74283. As you know, that all the ICs that we are using belong to the 74 series. So it all starts with the 74. But the IC number is 283. This is a full adder, 4-bit adder. So that means these are like A1, A2, A3, A4, and these are like B1, B2, B3, B4. It's pretty much do the same. So you will get a summation 1, summation 2, summation 3, summation 4. Don't forget the 4 is the highest, most significant bit for for A, for B, or for sum, and this will be the final carry. But inside this IC, this is exactly the same circuit that you have been seen in the last slide. Okay, so if anytime we use it, that's actually the the circuit we know for sure. Now, in the next couple of slides, we tried to do a little bit of a small maths to see whether we understand it properly. So what I did is I actually have drawn a full adder at the right side. I'm still using those 2 half adder, combining an OR gate and a sum. Okay, and plugging all the numbers that we are given in the question. So for an example, this is a 1-bit adder, right? Why? It's actually adding only one bit, right? Like one bit from A, one bit from B, and adding it, right? So you are given what the bits are, like A is 0, B is 0, and C in is 1, which is given to you here. So I pretty much wrote it here. And then you have to find out what will be the sum and carry at the very last stage. So that means you are adding 0 plus 0, so this should be 0, right? And then this should be 0 as well, but 1 is coming from the outside because this is given to you, right, in the question. And then you are adding 0 plus 1. The final sum will be 1, and this is 0, and this carry is 0, so that means the final carry will be 0. So you will be selecting option number C. So pretty much, in the questions you'll be given a couple of options, and you have to select the correct option based on the inputs you are given. Okay. Again, combining to half error to make a full error, a single error. So if you look at similar example, but this time this is a 4-bit error that we have just seen in the slide. Now let's say I have a 4-bit error, and then I'm giving both of the numbers here. A is given like 1110, B is given like 1101. Now let's recall what is this. Now this is my A1, right? My A1 is 0, A2 is 1, A3 is 1, A4 is 1, right? Similarly for the B, this is my B1, which is 1, right? B2 is 0, B3 is 1, and B4 is 1. Okay, so I plugged all of those values here. So once I plugged it, I actually did the calculation. So I assume that my initial carry is 0, because if nothing is mentioned, that means there is no carry at the beginning. Usually there is no carry at the beginning. So I pretty much did the addition. So what I did is, every time I added 0, 1, 0 for an example here, so I know that my sum should be 1, right? You are adding 0 plus 1 plus 0. Sum should be 1, and there is a carry of 0, which actually is going to the next column, right? And the next column you are adding 1 plus 0 plus 0. Again, the sum should be 1, and you are propagating the carry to the next column. So you pretty much do the same thing every time. And then the question was asked, the question is given like, what is the logic level at the point P? Now, what is point P? If you look at this, we actually said this is my P, right? Which is the carry out at the third error, right? So that is 1. So all you have to just say, okay, that is 1 or 0. So look at the question carefully, because we just mentioned different points. And every question it will be asking different, the low, what is the logic level of those points, okay? Any question here? Yes. These three adding and getting the sum, yeah. Okay, so we have 3 small quizzes for this part. Again, in all these quizzes, we'll be actually practicing the full adders and half adders. At the beginning, it will be half adders, and the later ones, it will be full adders. Now, all these quizzes are also designed so that we understand our lab 6, because in the lab 6, we'll actually build a circuit, okay, for this full adder. Now, the circuit also will be able to do the subtraction in addition to the performing the addition also, okay? Now you might be wondering, we are talking about the adder, how we can do the subtraction. Let's recall how we do the subtraction. Remember at the very beginning of the class when we learned about the binary subtraction, how we did the subtraction. Remember we had a couple of steps, and then what do? We just flip the number first, and then to make it a 1's complement, right? And then we add 1 to make it 2's complement, and at the very last step we actually add both numbers. So if you recall that steps, we actually have never done any subtraction. We did all additions. So that means binary subtraction actually can be done using only addition, okay? So this lab will also do the same. So we actually will build a circuit which can do the both, like addition or subtraction, based on our choice, okay? So let's finish these quizzes, then we can start the lab. And this lab is just one single part, a single lab, lab 6, which will be due next class. But this is a little bit longer than any of the previous lab that we have done until 5B. So that's why what we did is, instead of just having the circuit and schematic that we already have in POS, we'll also give you a procedure, okay? In the procedure, you can actually follow the steps. That, okay, procedure will tell you, you already have the schematic, but procedure will still tell you, okay, let's do this. I'm saying, connect this wire with this pin, okay? So that you have some more control on how to build the circuit. Since this is the first time, you will be building a little bit bigger circuit than you have seen until this point. So let me stop this presentation and let's try the quizzes first, and then we'll try the lab, which is due by next class.